the average credit card debt carried by undergraduates, and they mean all undergraduates, is normally distributed. This is the population. It's normally distributed. It has a mean of 3173 and a population standard deviation of 1120. What is the probability? So I'm looking for some kind of an area as my answer, that a randomly selected undergraduate from the population, there's no samples here, who is a credit card holder, has a credit balance less than, so I'm looking for an X person, a randomly selected person, who has a balance less than 2,700. Okay, so this is my population. Does it say anything from a sample of 10 people, from a sample of 200 kids? Nothing. So this is the one. You would start like this. You'd make your curve. Here's my 3173. I want to work this all out so that I like this because you can actually see the difference between a sample and a population. So add your 1120 all the way up and all the way down. Since we're going less, I just went one way. So now I can find my 2,700 in here somewhere, and I know that it's less than. So if you were going to guesstimate this, what percent would you give me? 45? Okay?
45.
45? Somewhere up, like, but we agree less than 50.
Yeah.
And we agree it's probably at least 40 or so. So now, we take our regular z-score, because this is for the population. Again, no sample size in here. Nothing was said about a sample. It was said about all undergraduates. They didn't use the word all, but we know that it's all undergraduates. They picked one randomly selected person, not a sample of people. So now, we plug this in. We know this has to be negative, because we can see that it's negative. We put our regular standard deviation under it, and we get a z-score of negative 0.42. We look this guy up, and we find this area to the left of this. Well, 33.72%. The probability that I will pick a person who has less from the population, who has less than 2,700 on their credit card, is about 33%, 34%. And you guys are in the ballpark, 45. We knew we were less than 50. Okay? Now, population. Scenario changes a little bit. We now randomly select 25 card holders. This is a sample. What's my N?
25.
If I tried to go to my population and pick N, what would my N be for my population? You don't have one. So that also tells you that's got to be a population, not a sample. But here, this 25 means something to me. I have a random sample of 25 credit card holders. Now, what is the probability, the same statement, that the mean credit card balance, that they didn't ask what the mean was here, they just asked a credit card holder for population, that the mean, the average of all those, would be less than, so I'm going to write it as a mean, less than 2,700. So we got a little bit of a change here. We're now taking a sample. When we take a sample, what's going to change? The mean or the standard deviation? Standard deviation. So my sample mean is still going to be 3173, but my population standard deviation is going to change. It's going to be 1120 divided by the square root of 25. We just made this guy a little smaller. So you're, I don't think I wrote it down. Yep, 224. Look where my standard deviation went for my sample. Smaller. A lot closer to the mean. Now, if I draw this curve, I still got the same mean. That's not changing. But now, if I go down here, and I go down, this gives me 224. I get 2949, 2725, and 2501. Look where I am now. My 2700 is now over here somewhere. So tell me, give me a guesstimate of what you think that probability would be. Would it be smaller than 34% or larger than 34%? Smaller. Okay? So because this has an opposite effect when it comes to the positive side. I'm going to use almost the same z-square formula. I'm going to start like this, but we're just going to change it. We've got the sample mean, and we have to divide by the square root of n. So my sample means is 2700. This part looks the same, except for down here. We say 1120 divided by the square root of 25. And we get a z-score of negative 2.11. And we said it would be just slightly to the left of the negative 2. We look up the area, and the area is about 2%. 2% probability that we will get a sample of 25, whose average, whose mean balance is less than 2700. So do you see the difference between the population and the sample? Because certain keywords we're looking at. This doesn't have any n, no n. They talk only about a population. And they do have to tell us that their population is normally distributed. Down here, they didn't have to tell us here only because we used that population up there. So if that population was normally distributed, then any samples you would have was. And that's only because it was hooked to this problem. But otherwise, they would have to tell you if it's less than 30. They would have to tell you normally distributed. Or your n has to be greater than or equal to 30. But we've got just a little bit of a change here. This you notice, this you notice. I like this problem because it shows you the difference between sample and population. Okay? Okay. Let's go back now and finish up I think we have maybe one or two problems left. As a matter of fact, what if you guys do try it 6? You're going to compare, let's have you guys do this. Compare your population to your sample. Somewhere it's here. Let's have you do try it 6. You're going to compare a population to a sample. I want to see both of them. All right, how do I know that the first part is dealing with a population and not a sample? There's no sample size, and it doesn't say sample. And it says a randomly selected computer monitor. A randomly selected, not a sample of 10, of 20, of 50, of 100. So, we start with this. We have a mean of 190 and a population standard deviation. Since they're talking about the population, then we know that that's a population standard deviation. What is the probability? Again, probability, I'm looking for an area that a randomly selected computer monitor costs less than 200. X is the computer monitor. Okay, so I build my chart. Okay, my 190 goes in the middle, and I go up 48. Hopefully I did this one. I only went up a little bit, just to get to 200. So if you add 48, this is 238. Now, I want to be less than 200. So 200's in here somewhere. So give me a guesstimate. What are we looking at? 55? It's got to be over 50. So somewhere. So I use my z-score formula. I've got my population going on here. I say z is equal to my x value minus my mean for my population, which makes me positive, and that's true, over my standard deviation. So I get a z-score of 0.21, which puts me between the 0 and the 1. I look at my area to the left, and it's 0.5832. So there's about a 58% chance that my randomly selected computer monitor that I select from my entire population will cost less than $200. Okay. Population. Here's my sample situation. You randomly select 10 LCD computer monitors. What does 10 represent? Sample size, and what variable? N. So now I know I have a sample. My mean is going to stay exactly the same, but now my standard deviation is going to change. It's going to be the standard deviation divided by the square root of n. Question?
The probability statement is still the same.
Still the same. Still the same. It's just one I pulled from my population, one I pulled from this group of samples. And notice how they say, what is the probability that a randomly selected computer monitor? What is the probability that the mean cost, their mean cost? Mean means you have more than one thing, right? And you average them together. So that's what my sample means, the sample. But probability statement, exactly the same. But now, well, I shouldn't say exactly. The only difference is instead of the x, you have an x bar. X bar means that's my group of means that I took from that sample. But the thing works the same way. So now, your standard deviation is going to be your 48 divided by your square root of 10. It's just going to shrink this down a little bit. So we get to 15.18. If we do this out, just because I want you to get a good feel for this, and we go up a little bit. Actually, we have to go to 200. So I'm over here, like 205.18. 200 is right near there. Should I expect this to be more or less? I know it's kind of hard to tell because you're still within the 0 to 1, but this one you were a little bit closer to the 190 than you were this guy. This guy, you're almost to the 205. So, excuse me, do I expect this to be more or less? More. So your formula is almost the same, except we're using your sample mean and we're changing your standard deviation. So your sample mean is still going to be 200 minus 190, and the bottom is the part that changes. So now I get a z-score of 0.66, a little bit higher than what I had before, because I'm a little closer in there. I look the area to the left, and it's almost 75%. It's a 75% chance that I will pull a sample whose mean, whose average cost is less than $200. Within that sample of 10, I'm looking for their mean. So can you see the difference between population versus sample? That's the whole thing of this unit that we're doing. We're doing the sample part. How does it differ from what we've been doing? Population versus sample. Is if you go to look for an N is not there, chances that you can do this. All right. The mean room and board expense per a four-year college, for any four-year college, is $9,126. Now, that statement they made is for a population, for any four-year college. They don't have to use the word any, but this is your population. Now, they said, you randomly select 9 four-year colleges. So what does 9 represent? N. Good. So now, instead of dealing with the population, I'm going to deal with the sample. What is the probability? Probability means area under the curve probability that the mean, how do I represent a mean? The mean, the average, like when you do it in your calculator for L1, what does it say up there? X bar is less than $9,400. Assume that the room and board expenses are normally distributed. They're going back to your population with the standard deviation, and this is from your population. They're going to tell you that your original population is normally distributed. So now when we take 9, we know that those 9 are in a normal distribution. So we know our mean for our population is 9126, and we know our standard deviation for our population is 1500. But we had an N, and we have a mean in our statement. So we need to find the standard deviation for the sample. This is the major difference. So we take your standard deviation and we divide it by the square root of 9, which is 3. So we can find your standard deviation for your sample. Okay? Okay, now, instead of doing your graph 2 ways, because then you'll have to redo your axis right in the middle, we only graph to the sample. So we put the mean in the middle, that's not going to change, and we want to know where 9,400 is. So just keep adding 500 until you hit that. So we're good just labeling 1. I just want you to get a feel. Where is your z-score? Approximately like where your percentages are. So if I'm looking for 9,400 somewhere here to the left, give me a guesstimate. 58, good, I'm above 50, I'm somewhere above 50. We didn't do any to the right yet, but if we did it to the right, and we guesstimated 40%, we would know that when we looked up our area and it was bigger than 50, we would know we had a problem and we would subtract it from 1. So your z-score formula now is the one for your sample. So we're going to say the mean minus the population mean, puts our z-score to be positive, take the standard deviation, divide it by the square root of 9. So now your z-score should come out to be 0.55. When you look up the area to the left, you're about 71%. And it was a little higher than Marissa's estimate, only because that little piece from 0 to 1 contains 32%. That's the biggest part, plus or minus 1. But guessing over 50 is what we were looking for. Because if this said, what is the probability that it's greater than 9,400, and we went through all of this work, and we said greater than 9,400, and you put it here, and you would guesstimate, maybe 40%, because it's less than 50, right? If you came down here and saw this answer, what would you know to do? Subtract it from 1. So that's why your graphs and your guesstimates are important. Then you would know to subtract it from 1. Okay? Do we have any questions? So let's have you do page 269, 272, 27, 29, 31, 33, 36, 37.